Okay, in this last part of electromagnetism, we will be zooming directly into the applications of electromagnetism in DC motors. Okay, so let's move on. Okay, so this is a very simple diagram of how does a DC motor works. Okay, so a DC motor actually converts electrical energy into mechanical energy, specifically into kinetic energy. I use electricity to produce a turning effect on this rectangle coil. And why does this rectangle coil turn? It's because of interactions of the magnetic field caused by the magnet, as well as the magnetic field caused by the current carrying conductor. In this case, it will be this rectangle coil. So these are the main components of a DC circuit. Okay, number one, you have a rectangle wire coil over here, which is labeled as A, B, C, D. Okay, and then this rectangle coil will be placed in between two permanent magnets, okay, with a north pole and south pole at one end. Okay, because I want interactions of magnetic field caused by magnets and the current carrying conductor. Okay, and one very important features for DC motor is that they uses a split ring commutator. This split ring commutator is very important to ensure that this rectangle coil will continue to rotate in the same direction throughout the entire time that the motor is switched on. Okay, we will go in depth to elaborate on the purpose, on the function of this split ring commutator, but you need to learn how to spell the split ring commutator as well. Okay, and then between the two split ring commutator, there is carbon brushes, which is labeled by X and Y over here. Okay, carbon brushes are used because this split ring commutator will keep turning, and then I need to have an electrical contact with the wire. But I cannot just have a bare wire here and then my split ring keeps turning. There will be a lot of friction generated. So usually the carbon brushes are put here so that because it's a brush, the split ring can turn without any friction. And carbon is a good conductor. It can conduct electricity. So I still provide the electrical contact with the split ring. Okay, and at the same time, minimize the friction between the electrical conductor and the split ring commutator. Okay, so for this chapter, I'm going to use the Evans notes, okay, to illustrate how does the DC motor works. So I'm going to pause the video here. I'm going to stop sharing here and I'm going to share with you the Evans notes. Okay, so you can see on my screen, okay, I have the Evans notes over here. Okay, so this is the DC motor. Okay, it makes use of turning effect of coil with a direct current in the magnetic field. Okay, so let's go to the one with a split ring commutator. Okay, so why is there a force acting on the coils? Okay, whenever current flows through it, as given by the explanation over here. It says that, okay, so you have a coil over here. Okay, so just now that diagram is a little bit 3D. Now I put my diagram into 2D. So you can see over here, I have a rectangle coil. In one side of my rectangle coil, the current is going into the page, and the other side of the coil, the current is going out of the page. Okay, and this will be the magnetic field generated by the magnets and by the current carrying coil. Okay, and you will see that there is an unbalanced magnetic field. Over here, I have a stronger magnetic field, and over here at the top, I have a weaker magnetic field. And because of this difference in magnetic field on this left-hand side, I'll produce an upwards force because the magnetic field always goes from a region of stronger magnetic field to a region of lower or weaker magnetic field. And similarly for this side, okay, I will have a stronger magnetic field here and a weaker magnetic field here. So the force will be downwards. Okay, because of this unbalanced magnetic field on both sides of the coil, I will produce a pair of forces on the coil. So the force will be up here and down here, and this coil, okay, will actually forms a clockwise movement, okay, about the axis of the coil, which is the center of the coil. So this entire coil will rotate about its center, okay, caused by these two forces. Okay, so how do I know the direction of force if I do not want to draw the magnetic field? Okay, we can simply apply the Fleming's left-hand rule. So to recap, okay, the thumb represents the father, okay, the force. The middle finger, the index finger represents the mother, magnetic field, and the middle finger represents the current, the child. Okay, so this is Fleming's left-hand rule, which we will use quite extensively in the DC motor. Okay, so let's go into the working principles. Okay. Okay, you look over here. Let's go into the first diagram over here. Okay, so what happens is, for easy reference and for you to visualize, okay, the split ring is colored with two different colors. Okay, so X is colored in blue and Y is colored in red. Okay, so I have a current connected to this rectangle coil. So a current will be flowing through this rectangle coil. So the first thing that you need to do is you need to determine the direction of the current flow inside this rectangle coil. Okay, so the current is going to flow from the plus side, plus terminal, through this carbon brush P, okay, and then through this split ring commutator X, and then go up the coil. Okay, so the current will be flowing in the direction of AB over here, and flowing in the direction of CD over here. Okay, so if I were to apply the Fleming's left-hand rule, okay, what I will get, okay, so this is a 3D diagram. In terms of 2D, it will look like that. Okay, let me make it smaller. Okay, so in this one, the current is going into the paper, so I see a cross. And then over here, the current is going out of the paper, I see a dot. Okay, so this is in the coil AB, and this is in the coil CD. Okay, and AB is connected to the X carbon brush, and CD is connected to the Y carbon brush. Okay, so X split ring commutator and Y split ring commutator. So if you were to apply the Fleming's left-hand rule with a magnetic field from north to south, and then the current going into the paper, okay, you will observe that at the side AB, there will be an upwards force. And on the side CD, there will be a downwards force. Okay, so it's explained here, carbon brush P, okay, over here touches half ring, the split ring X, and then current flow into the coil AB using Fleming's left-hand rule. This left-hand side will experience an upwards force. And on the other end, okay, where I didn't change my magnetic field, but I changed my flow of direction, my direction of current. So the force will be in the opposite direction. So the right side of the coil CD will experience an equal downwards force. So this will create a clockwise moment, and then the coil will rotate clockwise. Okay, then we move on into, so the coil will move on into this segment. Okay, the second picture over here. So I'll start to rotate clockwise. AB is still moving up, CD is still moving down, okay, because current is still going to flow to X, and then coming back to Y. Okay, so this is in the mid position. Okay, let's move on. It will eventually reach a position, okay, when the coil becomes vertical. Okay, so it's over here. When the coil has becomes vertical, AB is at the top, CD is at the bottom. Okay, at this particular junction, okay, if you were to take a look at this split ring commutator, okay, you will realize that the carbon brushes P and Q are actually not in contact with the split ring. That's why it's a split ring. There's a hole in the center. So what do I mean by that? When it's not in contact, okay, the current, there is no current that's going to flow through the coil ABCD. Current will be cut off. And when there is no current, there's only magnetic field, but no current, you will not have a force. So there is no force that acts on the coil. And with no force, okay, this coil by right, it should be stationary. But there is something called momentum, or the inertia of the coil. So the coil is initially moving clockwise. It doesn't want to stop moving, okay, or it has the momentum. So this inertia or the momentum will actually bring the coil slightly forward, okay, slightly more clockwise, because the coil doesn't want to change its original motion of moving clockwise. Okay, so the coil will rotate slightly beyond this vertical position. Okay, and you need to know that, okay, so I'm moving on. Once I move on slightly over this vertical position, okay, I hope you can see now the split ring commutator has changed position. Just now, X is in contact with P, Y is in contact with Q. But now once I turn, okay, P, carbon brush P is going to come into contact with the split ring Y, while X will come into contact with Q. But my current in the external circuit doesn't change. My current is still going up here to P, to carbon brush P. Okay, so if you are able to observe, the current now flows from DC to BA. Just now the current is flowing in this direction. AB to CD. But now because the coil has switched over, okay, but my direction of current doesn't change over here. So it is still into the paper on this side, but just that this side now, the coil is no longer AB, it has become DC. The coil has now becomes DC instead of AB. Okay, so it's the same. On this side, you will see that, okay, the current is still going into the paper, and on the right-hand side, the current is still coming out of the paper, okay, because of the split ring commutator. Okay, and so now what is going to happen? So I go to the words first. So let me zoom out a little bit. Okay, so it says that the half ring Y will now touch P, X will touch Q. The current in the coil is reversed. Just now the current is flowing from AB to CD. Now the current is flowing from DC to BA. So ABDC changed to DCBA. So the current has reversed. Okay, but again, based on Fleming's left-hand rule, the left side of the coil will still experience an upwards force, while the right side of the coil will still continue to experience a downwards force. And again, this pair of force will cause the coil to rotate in the clockwise direction. Okay, so the coil continues to rotate continuously. Okay, so I will continue to rotate until I'm in the flat position. I am still, this side DC will still experience up and AB will still experience down. Okay, it will continue all the way until it reaches the vertical position again. Okay, and the whole cycle will going to repeat itself again. Okay, so I go into the function of a split ring. So the function of a split ring commutator is to ensure that the current in the coil will be reversed every half a turn. Okay, when my coil flips 180 degrees, half a turn, one full turn is 360 degrees. So when the coil AB move on the left side goes to AB on the right side, we say that is half a turn. Okay, the current in the coil will have reversed from flowing from ABCD will become DCBA. Okay, so it will then cause the left side to always experience a upwards force, and the right side to always experience a downwards force in this case. Okay, or the left side will always experience a force in one direction, and the right side will experience an equal but opposite force. So the coil will always continue to rotate in one direction. In this case, it's the clockwise direction. Okay, so next we'll move on to some of the how can we increase the turning effect or moments of this motor. So we can increase by increasing the number of turns in the coil, because this will increase the force that acts on the coil. When there's a larger force, there'll be a larger moment. Because of this formula, moments is force times distance. So to have a larger moment, I can either increase the force or the distance, or I can increase the magnitude of the current by adjusting the rheostat. Okay, so this will increase, or I can increase the EMF by adding more batteries. Okay, so again, this will increase the force, increase the strength of the magnetic field by using a stronger magnet. This will increase the force. Okay, or inserting a soft iron core within the coil to increase the magnet, to concentrate the magnetic field. This will again increase the force. Okay, so these are the same as the forces acting on any current carrying conductor. Okay, I can just do any of these steps. Okay, the last step is to increase the width of the coil. Okay, so you can see that this is the width. The width is actually between this green dot and this green dot. Okay, if I were to increase this width, I'm actually increasing the perpendicular distance between the force and the pivot. The pivot will be right in the middle at the center. Okay, and when will I have maximum moment? Maximum moment is when the coil is horizontal, because when the coil is horizontal, the perpendicular distance between the force and the pivot will be this red line over here, and this perpendicular distance will be a maximum. If my coil is not in the horizontal position, it's slanted, diagonal, or vertical. When it's vertical, there will be no moments. Okay, because the perpendicular distance is 0. But when it is slanted, you will see that the perpendicular distance is again between the force and the pivot. It will be shorter. Okay, it will be shorter over here because based on Pythagoras theorem, okay, this length will be longer. The hypotenuse will be longer. Okay, so in the horizontal position, the perpendicular distance is the maximum, and the magnetic field strength, okay, there will be more magnetic field strength interacting with this coil because it's horizontal. Magnetic field strength is also maximum. The force experience will also be maximum. So the best turning effect is when the coil is in the horizontal position. Okay, so we have covered the first part of how a DC motor works. Okay, let's move on to a section where we don't use split ring commutator. We look at how does a DC motor works when there is no split ring commutator. Okay, so let me scroll down. Okay, so now it's without a split ring. Okay, so let's observe this. Okay, so now I don't have a split ring. I still have the same battery connected to the coil ABCD. So at the first stage, the current still flows through ABCD. So same, using Fleming's left-hand rule, the left-hand side, which is coil AB, will experience an upwards force, while the side CD will experience a downwards force. Just take note of where do I draw my forces. The forces must always be drawn on the wire because it is the wire that is experiencing the force. Okay, so over here. Okay, so this is the same as before. This coil of wire will turn clockwise. Okay, but then after that, okay, when it reach a vertical position, it looks like this. Okay, in the vertical position for DC motor with split ring commutator, the carbon brush is exactly at the gap of the split ring. So there will be no current flow and no forces acting on the coil. But in this case, okay, because there is no split ring, the current will still continue to flow, okay, in A, B, C, D, in this direction. So, so there will still be a force acting on the coil. AB will still be upwards and CD will be downwards, okay? But there is no perpendicular distance, so no moments will be created. Okay, but again, due to the inertia or the momentum, the coil will still continue to rotate past this position, slightly beyond this position in the clockwise direction. The difficult thing comes when it rotate past this vertical position. Okay, you will see that because there is no split ring, the current will still continue to flow in A, B, C, D. It doesn't change. But now AB is on my right side. So when AB becomes on my right side, okay, and because of the current flow, AB will still experience an upwards force and CD will still experience a downwards force. So now because of this force, this coil will not rotate clockwise. This coil will rotate anti-clockwise. So you can read here, at this position, the pair of force will produce an anti-clockwise moment. So the coil will again be rotated back to the vertical position. So eventually, okay, it will again surpass the vertical position slightly because of momentum, but it will again rotate clockwise, anti-clockwise, clockwise, anti-clockwise, and eventually it will come to a rest in the vertical position. So this is what happens when you do not use a split ring commutator. Okay, so again, the same thing happens for how do I increase the momentum or moments. Okay, sorry, how do I increase the moments? It's the same way. Okay, but just take note that the coil cannot turn continuously in one direction. That is why a split ring commutator is required for a DC motor. Okay, DC motors are used in appliances that needs to have rotational motion. For example, your fan, you switch on the fan, Okay, it converts the electricity into kinetic energy to spin your fan blades. Okay, you don't see a fan that is being spin clockwise and then anti-clockwise, clockwise, and clockwise, and then eventually stop spinning. But this will happen if you do not use a split ring commutator in your DC motor. Okay, so this is basically the working principle of DC motor. I will show you a video. So let me. Okay, let's watch a video.
Many objects around us operate on electricity. However, they will not move continuously without this component, the split ring. Can you recall how the magnetic fields from the current carrying coil and the permanent magnets interact? As the resultant magnetic forces act from the stronger to weaker magnetic field regions, the turning effect of the coil in the DC motor is produced and cause the coil to turn. Now, we shall focus on the function of the split ring. Let's connect the current supply directly to the coil without the split ring. What do you observe? At the coil's vertical position, the directions of the magnetic forces are acting vertically upwards and vertically downwards. As both equal forces act in opposite directions, no turning effect is created. As a result, the coil stops spinning. Now, let's observe our DC motor setup with the split ring. The DC motor setup spins continuously. We will refer to the DC motor simulator kit to understand how the split ring enables the continuous motion. The magnetic forces always act vertically upwards and vertically downwards to create a clockwise moment as the coil turns. When the coil reaches its vertical position, the gap between the split rings prevents electrical contact with the carbon brushes. As a result, no current passes through the split ring. There is no magnetic force and therefore no turning effect. However, the momentum causes the coil to continue its motion. As either half of the split ring crosses over to the other carbon brush, current passes through it again. Note that the current changes direction, and consequently, the magnetic forces also change directions. Once again, the forces create a clockwise moment, allowing the coil to turn in the same direction as before. At every 180 degrees, the split ring changes the current direction. This changes the magnetic force direction to ensure the continuous motion of the coil in the same direction. The next time you enjoy the breeze from an electric fan or travel on a train, remember, it is the split ring in the DC motor that keeps them moving in the same direction.
Okay, so that's it.